This is presentation 14. I'm Aaron Hoover with Jose Almonte and Shawn Stewart, and today our presentation will focus on the use of polymer semiconductors in artificial photosynthesis. Because of humans' ever-increasing energy use, the fuels stored in our planet by photosynthetic pathways have begun to decrease faster than they can be replenished. In recent years, scientists have looked to artificial photosynthesis as a possible solution to this global dilemma. Artificial photosynthesis, which aims to mimic the sunlight-harnessing energy production of natural photosynthesis, can be done in a number of ways, utilizing several different reagents and materials, including polymer semiconductors. In this presentation, I will give a quick overview of natural photosynthesis and explain why artificial photosynthesis is necessary. Jose will talk about polymer semiconductors and the advances in artificial photosynthetic pathways. Shawn will then discuss the challenges involved with creating artificial photosynthetic systems and what can be done about them. Before I talk about the artificial version, I should briefly discuss natural photosynthesis. Photosynthesis is a biochemical pathway through which energy from sunlight is used to convert carbon dioxide to carbohydrates and water to oxygen. This process occurs in the chloroplasts of plants, algae, and some bacteria, and is responsible for the abundance of energy stored on Earth, largely in the form of fossil fuels. As a simple overview, photons from sunlight are absorbed by chlorophyll pigments in the thylakoid membrane. Energy from these photons is used to produce ATP. At the same time, water is broken down into oxygen and hydrogen ions, which releases electrons that are responsible for producing NADPH. After the light reactions are complete, the ATP and NADPH are utilized by the Calvin cycle in dark reactions, which are responsible for the production of carbohydrates from carbon dioxide. The oxidized NADP plus and the dephosphorylated ADP are then returned to the thylakoids to repeat the cycle. So what makes artificial photosynthesis so important? Well, natural photosynthesis has been described as the most important chemical reaction on Earth. It is responsible for Earth's large store of fossil fuels and for oxygen production, but now it is no longer sufficient for humanity's needs. The world's fossil fuel use has been increasing relatively steadily for the past 40 years, and now energy stores are being used faster than natural processes are able to replenish them. In addition, the world's energy demands are projected to double by 2050 due to population growth and increased industrialization. Unfortunately, humans do not have billions of years to produce the energy needed for our society. Instead, efficient, renewable energy sources must be found to bridge the energy gap. This is why scientists have been researching artificial photosynthesis. A result of humans' excessive use of fossil fuels is a release of carbon dioxide into the atmosphere. Carbon dioxide accounts for more than 80% of the greenhouse gases released by human activities and is a major contributor to global climate change. Before the Industrial Revolution, the carbon cycle balanced the levels of CO2 in the atmosphere by cycling carbon through the air, land, sea, and organisms. But since then, the CO2 emissions resulting from industry have become more than nature can efficiently handle. Although decreasing greenhouse gas emissions has been a focus of most stable governments for many years, the idea of sequestering CO2 from the atmosphere to combat climate change has also been discussed. Luckily for the scientists studying artificial photosynthesis, this is exactly how photosynthesis works. If the science of artificial photosynthesis were perfected and able to be commercialized at a global level, it would provide a clean and renewable energy source that not only has no carbon emissions, but sequesters CO2 from the atmosphere, a big step in the fight against climate change. A main reason why artificial photosynthesis may be of great importance is the possibility of finally bringing about the hydrogen economy. As I mentioned before, securing an adequate supply of fossil fuels may be a problem in the near future, not to mention the complications that unchecked climate change may cause. The use of hydrogen as fuel, if it could be done economically, would be the answer to all of our problems, and artificial photosynthesis may be able to help. A major step in hydrogen fuel cells is the production of hydrogen from water, which can be achieved through the electrical potential produced via artificial photosynthesis. Further advancement in this technology could result in a worldwide availability of an emissionless, renewable, and readily available energy source in the form of water.
Hello, this is Jose Almonte, and I'm going to talk about some of the previous developments that led to the use of polymers in artificial photosynthesis. And there's no better place to start than to discuss how nature does photosynthesis. Plants are able to capture 6% of the solar energy that hits their leaves. And that is pretty much the basis we're going to use to compare our own human designs as to how efficient they are. Humans have been able to design photovoltaic systems that are 3 times as efficient as plants' leaves. But when it comes to polymers, there is a barrier that must be overcome before we are able to use them for photosynthetic purposes. And that is that in order for an energy conversion system to be commercially viable, it must be able to store at least 10% of the solar energy it receives. And as of right now, it has been reported that the highest polymers have achieved is a 9.5% efficiency, according to a 2012 study by SNR. In order to overcome the 10% threshold that holds polymers back as a viable source of photosynthetic energy, scientists and developers have focused on one particular step of the photosynthetic process, which is water splitting, also known as hydrogen evolution, which is simply the division of water into its component elements of oxygen and hydrogen. Hydrogen is the important of the two here, since it's a highly reactive element and a main component of fuel cells, which are sources of alternative green energy that are being worked on nowadays. Now let's discuss one non-polymeric method we've used in the past to achieve water splitting. In 1967, Akira Fujishima made some research that proved that titanium dioxide and metal oxides in general were able to achieve water splitting. But titanium dioxide has a very big drawback. It has very poor absorbance of visible light, and thus interest in that compound has languished over the years. However, our own Penn State's Dr. Thomas Maluk still works with this compound nowadays and has found that he can increase the efficiency, the ability of the compound to absorb visible light, by adding a dye of ruthenium trisbipyridine. Another characteristic which has been found to increase the light absorbance efficiency of certain chemical species, including titanium dioxide, is mesoporosity. Mesoporosity is a characteristic of certain chemical compounds of having pores of 2 to 50 nanometers in diameter. This has been found to increase the light absorbance efficiency by 3 or 4 orders of magnitude. Now let's discuss some of the achievements that have been accomplished by using polymers for water splitting. Polymers have an advantage over other chemical species because they are closer in complexity to nature and can be modeled to function as light antennas and has been demonstrated in various studies. These light antennas are analogous to chloroplasts in plants. The first semiconductor polymer that has been reported to be able to split water by functioning as a light antenna was polyphenylene, but it only worked with ultraviolet light, and we want our polymers to be able to absorb all of the sun's light spectrum, or at least as much of it as possible. In Australia's Melbourne University, Kenneth Gigino and his team work with phenylene-vinylene derivatives, which are able to absorb light more efficiently, but they are not optimized for the splitting of water and the production of useful fuels such as hydrogen, so more work needs to be done in that regard. Another compound which has been found to be able to function as a light antenna is mesoporous graphitic carbon nitride, or MpGC3N4. As you remember, the mesoporous characteristic of certain compounds allows them to be able to absorb light more efficiently than non-mesoporous compounds. Mesoporous graphitic carbon nitride also has open crystalline pore walls and a large surface area, which make it really useful for absorbing light. It has the optimal surface area of 68 to 373 meters squared per gram, and any more than 373 is detrimental to the light absorption process. It works up to 590 nanometers of light wavelength, which allows it to absorb most of the sun's light spectrum. All of the previously mentioned characteristics make MpGC3N4 one of the most viable polymers found to be able to cause water splitting by using sunlight. However, there is one more recent development that we feel should be mentioned even though it is non-polymeric in nature, and that is Daniel Nocera's synthetic leaf. As its name implies, Daniel Nocera's synthetic leaf is a device that absorbs sunlight and uses it to split water in order to obtain energy. It is mostly made of silicon, cobalt, and nickel, and it is 10 times as efficient as a natural leaf. It can also operate continuously for 45 hours, and it uses silicon as the semiconductor that absorbs and traps light. The interesting part about Nocera's design is that the silicon core could be easily replaced by a polymer that has been designed to be a more effective light antenna, such as the previously mentioned MPG C3 and 4. By doing this, we could be able to design more efficient synthetic leaves that could help us overcome our current fuel crisis and provide us with commercially viable, renewable green energy.
While the possibilities of artificial photosynthesis can be greatly beneficial, there are difficulties that must be overcome to create such a system. The four main challenges that scientists face are capturing photons, separating charge, linking together a photocatalytic cycle, and self-repair. In order to capture photons, sunlight must be concentrated to efficiently convert it to useful energy. Nature completes this task through light harvesting with a highly organized array of chlorophyll molecules. The efficiency achieved by the natural array has inspired scientists to create an artificial system which will operate with similar efficiency. However, nature's system is extremely complex and nearly impossible to mimic. It transfers excitation energy between weakly coupled chromophores through the Forster mechanism. This mechanism involves through-space interactions. Artificial systems utilize electron exchange interactions between more strongly coupled chromophore arrays. These artificial systems can take advantage of through-space and through-bond interactions. Some of the first artificial light harvesting complexes were covalently linked porphyrin dimers, which led to studies of arrays, dendrimers, and polymers. All of these facilitate fast and highly efficient energy transfer. The main goal for this array is to transfer the energy throughout the system, but ultimately end up on one chromophore. This requires an energy gradient to be set up within the complex using a careful choice of chromophore placement. As seen in the figure, this artificial system is moving the energy to one end of the light harvesting molecule. Now that the photons have been harvested, they are directed to a reaction center complex, which I will refer to as the RCC. Original research into artificial RCC molecules used dyads, but these allowed fast charge recombination, which is something that should be avoided to have an efficient system. Then reports of the first molecular triad were produced, and they led to the realization that the rate of electron transfer decreases exponentially with increasing separation between reactants. This discovery led to larger molecule research into triads, pentads, and so on. The photons are then used to drive an electron transfer reaction that causes a charge separation across a lipid bilayer membrane. Nature does this through short-range jumps that tend to avoid rapid charge recombination of the positive and negative charges. The goal is to transfer electrons from one side of the molecule to the opposite as quickly and efficiently as possible so the charges become spatially remote. There is a delicate balance in using long polymer chains versus complex supermolecules. Long polymer chains are simpler to synthesize but are not always the answer because they allow for fast charge recombination. On the other hand, taking the time to create a large, complex supermolecule could lead to errors in the design and to waste all of the time spent synthesizing the molecule. Simple dyads would be advantageous to use as compared to large supermolecules in terms of synthesis, but something is needed to slow down the fast charge recombination that occurs. That something has not yet been discovered. Chemical potential feedstocks can be supplied by photochemistry, which provides direct access to strong oxidizing and reducing species. To complete photolysis, there are two problems that need to be solved. One is that the species made in this process only require a one electron transfer, but formation of a stable species often requires 4 or more electrons to be transferred. This problem requires charge accumulation to couple the photolysis to produce stable products. The other problem is avoiding back-to-back reactions between products. This must be done by designing and linking two cycles, one that forms fuel and another that provides the oxidizing agent. Many photolysis systems have been optimized to produce small molecules. However, in doing so, more problems arise. The major issue that must be overcome in this is the need for improved oxidation catalysts. For instance, there are no known effective catalysts for carbon dioxide or ammonia reduction. While photooxidation of persulfate to oxygen has been achieved, the harsh conditions destroy the chromophores quickly. These photolysis systems also produce hydrogen and oxygen that can mix in the gaseous state. This is undesirable, and there are problems collecting hydrogen over large areas. A solution to this problem can be seen in the figure. Here, oxygen generation is coupled with a 2-electron reduction of a relay quinone, Q, which combines with hydrogen to make QH2. This substance is then utilized in a separate cycle in which the hydrogen evolving catalyst is localized at a collection point. Even though many difficulties are faced in such systems, they are the only viable option to storing sunlight as chemical potential at the moment. Self-repair is the last and most difficult of the 4 challenges faced in artificial photosynthesis. While biological systems have the ability to self-repair, there are virtually no man-made materials that can sense and repair damage that occurs during operation or from photochemical damage. This is a relatively new stage in the research of artificial photosynthesis, so solutions are limited. There are 4 possible pathways being looked at right now. These are redundancy, reservoir effects, excision and replacement, and on-site repair. Self-repair is a crucial step in developing lasting and efficient artificial systems. As natural resources deplete and CO2 emissions rise, we need to find a solution that can address both problems. One possibility is the use of artificial photosynthesis, specifically the use of polymers in these systems. While there are challenges in the creation of such systems, it is important to find a way to overcome them.